Welcome to Evolution Impossible, a production of 3ABN Australia Television. Our host is Dr. Sven Estring with special guest Dr. John Ashton and our panel.
Hello everyone, I'm Dr. Sven Estring. It has been great going on this Evolution Impossible journey together, where we are leaving no stone unturned to find out whether Darwin's theory of evolution could actually work. I'm delighted to be able to welcome back Justin Trosen. Good to have you here. And we're very privileged to have in Melvin Sanderling, who has a Swedish-Dutch background. Now, Melvin, I reckon if we go back far enough, we could find a Swedish common ancestor. And also, we have Jean-Ray Roux, who is a pilot. Glad you could drop by.
Good to be here.
And always here to give us good answers for our questions is Dr. John Ashton. Thanks for being here. You know, figuring out the age of something in nature is not always an easy task. However, there is one dating method that scientists tell us is really simple and very reliable, and that is radiometric dating. It's like reading the time off clocks in the rocks. But does radiometric dating really tell us the true age of the rocks? That's what we're exploring today. Now, guys, I just want to ask you, how do you understand radiometric dating to actually work?
Oh, look, you guys have it.
Well, I'm a bit scared to say anything, since in your introduction you said scientists say it's really simple. But when I read about it, I'm a bit confused. It has something to do with the decay, measuring certain decay in rocks and then dating the age, and I would need some more explanation on it, actually.
Excellent, John. Well, good to have you here. Can you fill in some of the details about how radiometric dating actually works?
Yes, well, there are materials that we call radioactive, and that is they slowly emit atomic particles of some type, and they actually, some of them change from one element into another element, so we call that the mother element changes into the daughter element. And
gamma rays and alpha particles.
That's right, neutrons, these sort of particles, or maybe a beta particle, an electron is emitted. So what we can do is the method involves very accurate chemical analysis of these isotopes. Now, what an isotope is, an element is defined by the number of protons or positive charges in the nucleus, but it can have different masses which are dependent on the amount of neutrons in the nucleus. And so an element is defined, as I said, by the number of protons, but when it has different number of neutrons, we call that different isotopes. Now, when it has different numbers of neutrons, it may alter the stability, and when it's less stable, it emits these particles and what we call radioactive. And so uranium is one of the classic radioactive materials, one of the first discovered, that had these properties. And so what scientists do is, by very accurately using mass spectrometers these days, measure the amount of one particular isotope in the rock, and then the parent isotope, and then they measure the amount of the daughter isotope. And in the meantime, they've measured the rate at which these elements have changed. So they've studied the radioactive material over a period of time, and they've measured what they call the half-life of the material. Okay. Now, this is a very important factor. This is the mathematical factor that is used to calculate the age. And so what it essentially is the time, measured in years usually, that it takes for half of the mother element to decay to the daughter element. And so if the half-life, say, was 5,000 years, after 5,000 years, half of the radioactive material would decay away. After another 5,000 years, another half of what remains has decayed away. So we now only have a quarter of that material. So again, from chemical analysis and mathematical equations, we can calculate on that basis, assuming that radiometric decay rates haven't changed, assuming that there's no leaching out of or removal of the mother parent element or the daughter element by some other means, it's only radiometric decay, then we can calculate the age of that particular rock that it's found in.
So you're counting the parent, the mother isotope, you're counting the daughter, and then you're putting it on the curve, and out comes the date for the rock.
Yes, that's right. And there's a mathematical formula in there, yes.
Fantastic. Any questions on that process?
Yeah, I was just wondering, like you mentioned a time of, for example, like 5,000 years, and in your book you describe certain other numbers that can span like billions of years for half-life reactions. How do they come up with the times? Like how can you measure that it's 5,000 years of the half-lives? How can you know that?
Well, I'm not an expert on atomic clocks, but I understand that with these atomic clocks that they can measure those particular half-lives. But that's an area I haven't actually explored the rate at which or the actual laboratory method of measuring those half-lives. But I have read the papers where they've noted that half-lives can change, for example. So under very high temperatures, they measure different half-lives, and also they measure different half-lives that appears in association with different sunspot cycles and this sort of thing, which is very interesting. And there's also the theory of you can produce accelerated nuclear decay. But anyway, that's a good point. I need to read up on the actual methodology that they use. Well, we do have very accurate atomic clocks. In the olden days, they used to measure radiometric decay rates using Geiger counters, which actually counted the number of particles. And so I guess by integrating, if we count the number of particles over an hour very accurately, and there are lots of particles involved, then we could actually calculate billions of years ages. So I'm sure it's just a physical calculation problem, but I haven't actually entered into that.
So it's fairly accurate, but it's really dependent on what kind of external circumstances could have influenced this half-life reaction over time.
Yeah, so I imagine that the measurements of the rate of decay are actually quite accurate because they're done in a controlled laboratory situation. We've got quite accurate machines now. What we can't control, of course, is the environment that those rocks are in. They're out in nature, and also we can't control, and we don't necessarily know what the conditions were in the past. And that's one of the big downfalls of radiometric dating, in that we have to assume that none of the daughter element is leached away, or that more of the daughter element is leached in, for example, also, and the same with the mother. So these are physical processes. You have elements in rocks, there's water and other fluids can be leaking through. So yes, there's a lot of issue.
Same thing with what we talked about last time, with the sedimentary rates and the erosion rates. We don't know what happened in the past.
Yes.
But they're still using the same erosion rates they're calculating or measuring for billions of years.
One of the ways they try to improve the accuracy of radiometric dating is a technique that has been used since the late 1980s, and that's called the Isochron dating method. So the methods for that particular form of radiometric dating, we can only date volcanic rocks, and the crystals in the volcanic rock often have, or sometimes have, radioactive elements in them. And there will be different mineral crystals in the rock. And so those different crystals have different chemical compositions, and so they'll be made up, they'll have different radioactive elements in them. So one of the things we can do in a rock is analyse, separate out the different crystals, and then individually analyse or date those different crystals in the one rock, and then plot those together. And if we get a pretty good straight line, in other words, the data from all the different crystals in the rock are matching up, then that gives us fairly high confidence. So that's the most accurate method. That's called the isochron dating method.
Are there any assumptions underlying the isochron method that we still need to be aware of?
Oh, well, they're the same assumptions as before. And you can get other problems too, in that, for example, how do we know there aren't mixing of much older rocks with younger rocks during the molten time, this sort of thing. I mean, it is fraught with a whole lot of assumptions, and this is what people, I think, just generally don't realise. Okay, we've got this result and we've got this measurement, and people automatically assume that it's correct. One of the classic things that I like to point out is that radiometric dating methods have never been validated for prehistorical dates. We haven't been actually able to validate the method, that the method is actually working. And this blows people's minds away. I've actually written and pointed this out, to sort of fellow scientists, because a lot of people think, okay, we get this result from a laboratory, it must be true. Well, in reality, chemical analysis is very different from that. I can remember seeing the results from government laboratory trials, or government trials of laboratories where we were testing the accuracy of laboratories, and where samples had to be analysed by the leading analytical laboratories, and the results were widely spread. And the sample was actually a known sample, and I can't remember how many labs were involved, but there were dozens of laboratories involved, and I think there were only 2 or 3 out of those laboratories that got the actual accurate answer. So this is something we need to measure. There's 2 things. There's the performance of the laboratory, but there is also the method itself. And one of the things is that radiometric dating method hasn't been validated.
But you say prehistoric ages, so that's going back the millions and billions of years. But what about, science has been very active over the last 200 years. So what about validating radiometric dating over that period? How has that worked?
Oh, yes. Okay, so this really highlights the problems with radiometric dating. Or one of the issues, and perhaps what I should highlight before I answer that is that typically when we date rocks, there are a number of different radiometric dating methods we use. We might use samarium, neodymium, or potassium argon, or rubidium, strontium, lead.
We'll have a quiz on those names later.
And what often happens is, depending on the method that we use, which are all valid radiometric dating methods, we'll get widely different answers for the same rock.
That's very unusual.
It is. So what generally happens is you have an age for a rock that is based on the fossil record ages that were based on estimates of sedimentation rates and the thicknesses of those layers in which the fossils were laid, the physical thicknesses. And so they estimated the ages. And so this gives us what is known as the standard fossil age, right? And that's the age that you'll find in the textbook. Now, if you find a rock that is associated with layers above or below of the fossils that we're finding, that are listed there in the textbooks, and it might be, say, 200 million years. And then when you start dating it, one method might give you 130 million years, another method might give you 250 million years, another method might give you 700 million years, another method might give you 1 billion years.
So sort of pick your age.
Well, what happens is when you're writing up your thesis, you say, well, I've got all these values there. 250 million years is closest to the fossil age of 200 or 220 million years. I'm going to put that in. So you record that result. And what is happening? But why aren't the other results considered? Why aren't the results that gave you 1 billion years? Usually uranium values, uranium lead values will give you billions of years for most rocks. So, and this is one of the problems. Now, the other thing is when we this has been done a number of times, when we radiometrically date rocks that we know the actual age from, so it's a volcanic eruption that occurred maybe 200 years ago, people have observed it, they go and chip out the lava and take the sample to the lab. These always come back as being dated hundreds of thousands to millions of years old, even though we know the rock was 200 years old.
And that's the question that I had, is when different methods are being used with all those names that you pronounced that I won't try, but they give these different answers, like really different answers. But they use the same principle. It is dating that half-life time reaction.
That's right.
And if that is fairly accurate in itself, but the answers are so, they can differ billions of years, where does that difference come from?
Well, I'm not sure, but I think one of the things is that when you look at the half-lives of a lot of those systems that are used, those half-lives are billions of years. And And so it seems to me very reasonable that you're going to get hundreds of millions of years as your answers. And I think the classic example of this was work that was done here in Australia, where samples were taken from the eruptions from Mount Noahoe in New Zealand, when it erupted in the late 1940s, early 1950s. And when those samples were analysed at one of the geoscience laboratories at the Australian National University here in Australia, the samples gave ages from memory ranging from about 130 million years, 300 million years, and I think 3,500 million years for rocks that we knew were 50 years old. Well, the analyses were done in the late 1990s, early 2000s. So at that stage, the rocks were only 50 years old, and yet they all gave more than 100 million years by different methods, by one of the best radiometric dating laboratories in Australia.
But what about the idea that the rocks might be 50 years old, but the chemical composition, the material might have been very old? Would that play into this calculation at all?
Well, it could do, but what it means is that it's useless in dating any rock, isn't it? If rocks that are only 50 years old date as millions of years old, and you pick up another rock sample and you get some millions. How old is it? Is it millions of years old? Is it 50 years old? And the thing is, that isn't just an isolated example. If you go to the standard, some of the standard radiometric dating textbooks, they cite these examples of where Hawaiian lava flows were being dated and so forth. And again, the standard explanation is, well, somehow there was some sampling errors, or somehow there was sort of some mixing, of the magma or something like that. But what the ratios were that God originally created, we don't know. It doesn't match. And when we compare that with erosion rates and all these other factors we can see, it virtually wipes out radiometric dating.
Now, one of the things that often happens in the general popular thinking, if I could put it that way, is that as soon as you hear radiometric dating, you think carbon-14 dating.
All right.
But they're the same class of dating method, but they're quite different, and there's some misunderstandings about carbon-14 dating. Can you just enlighten us on that topic?
Yes, okay. So carbon-14 dating is another dating method that actually doesn't, it works on a different principle. In other words, the radiometric dating, we calculate the age, but carbon-14 dating depends on so many variables that it itself has to be calibrated by some secondary method. So how carbon-14 dating works is this, that in the atmosphere, the upper atmosphere is hit by cosmic rays coming from outer space, which are charged high-energy particles. They collide with atoms up in the outer space area and generate high-energy neutrons. Some of those high-energy neutrons then hit a nitrogen nucleus. So nitrogen's one of the gases in the atmosphere there, and it has 7 protons and 7 neutrons. And what happens is sometimes those high-energy neutrons knock a proton out of the nucleus, leaving only 6 protons, which changes that nitrogen to carbon. It very quickly reacts with oxygen before it becomes carbon dioxide. But that is now carbon-14. Normally carbon is 12, 6 protons and 6 neutrons. But now it's carbon-14 and it's unstable. And it has a half-life of 5,730 years. And so after 5,000 years, we'll only have half the level. After 5,500 years. After 11,000 a bit years, we'll have only a quarter of the level. After 15,000 years, we'll only have an eighth of the level. So by measuring the amount of carbon-14 that we have, we can back calculate the age of things. Now, carbon-14 is very good for dating the actual fossils because they have carbon in them. So we can date the actual fossils that way. And but the thing is, we measure, back in 1950, they standardised the level of carbon-14 in the atmosphere. Well, since then it's been changing. We've had a lot more carbon dioxide come up, which is diluting it. The other thing is that the Earth's magnetic field repels a lot of the cosmic rays. And so the amount of carbon-14 that is present in the atmosphere depends on that carbon-14 flux anyway. In the past, we know the Earth's magnetic field has been decaying. It's decayed about 10% in the last 150 years, 6.5% since 1900, for example. And so in the past, a stronger magnetic field would have repelled more cosmic rays, which means lower levels of carbon-14, which gives us artificially longer ages if we base it on the current level, which is what we do. Now, how it works is that when a plant is alive, it's taking in the carbon dioxide and there's an equilibrium at the same level of carbon-14 as in the plant as in the atmosphere. But when it dies, or it's buried, and the same with an animal, there's no more interchange with carbon-14, so what's there begins to decay. And so it will have a lower level over time, and so that's how they calculate the age. But it's very interesting because after about 100,000 years there would be no detectable carbon-14 left. So if we find carbon-14 in something, it means it's got to be quite
less than 100,000 years old. Interesting.
And I think you mentioned in your book that there were some diamonds taken from the De Beers mine in southern part of Africa, and that these were carbon-14 dated, I think it was. Yes. They're estimated to be between 1 and 3 million years old, but like you mentioned, if they had carbon in them, they have to be, less than, how old was it, 100,000?
Yes, that's right, and that's a very interesting example because diamonds were meant to have formed when the continents formed under intense heat and pressure, and they're meant to be 1.5 to 3 billion years old. So it should have absolutely none. Wow. And of course, they began finding carbon-14 in diamonds, and this was seriously challenged. And so some very accurate studies were done at the University of California, Los Angeles campus, from memory, using one of the most accurate mass spectrometers in the world, and sure enough, carbon-14 was there in diamonds. And so that is powerful evidence that the continents can't be that old. And now, of course, they've carbon-14 dated dinosaur remains, and the same thing. They all, and sometimes they come out at around 20 or 30,000 years, and people say, well, that's still a lot older than the Bible dates, but that is just the straight age date. We haven't corrected for the lower values of the caused by the lower cosmic ray flux in the past. So that
one of the things that there's Christians in the world today who say, we want to believe in the Bible because it's changed our lives, made such a big difference, but also science has been so transformative in our society as well. And we want to integrate those two. And we would head towards something like theistic evolution, where God supervised or guided the process of evolution. Well, what's your thoughts on this concept or proposal of theistic evolution?
Well, I guess there's two aspects. You can have the theological aspect that it certainly doesn't fit with the concept of sin and death that the Bible talks about. But the other problem is, why are they doing that? Why do they believe that the earth is so old? And I think it's because they've been inculcated with this idea from radiometric dating of the long ages. But you're just bowing the knee to a false science then. We have so much evidence now that the earth can't be those hundreds of millions of years ages that the radiometric dating results give us. We know classically from erosion rates, we know from the soft tissue in dinosaurs, there's so many things that are pointing to this young age. And the fact then that we can find carbon-14 in coal and so forth. So to me, this whole concept of theistic evolution, that God had to bow the knee to evolution and produce it slowly over time, just doesn't fit the scientific data. Plus, why does God need to do that? He said He's spoken into existence. And the other problem too that we often forget is that evolution has major problems in terms of ecology, as we've talked about, in that you need the insects and the flowering plants need one another. There's a whole lot of ecological balance. The ecosystems, and it doesn't follow the lines of the evolutionary, phylogenic trees. So you're going to be, they're caught out. They're caught out with science, and they're caught out, in my view, with theology as well, what the Bible actually says.
Do you have any further questions on this topic of radiometric dating and theistic evolution?
Well, what you're saying with it's just the mindset of people thinking there's millions of years. Does that sort of correlate with the biblical account of creation, where they say evening and morning, or the Bible says evening and morning was the first day, but they claim that it was millions or thousands of years time period that passed?
Well, no, time is a fascinating thing, as we have mentioned just briefly. But no, there were 24-hour Earth days, and the whole universe was created in that time, because if you look at Genesis 2:1, it says, "And God was finished," and the whole host of them had been created then. And we talk about God spoke things into existence, and to me, that's very reasonable. I think a classic example of this is. Let's do an experiment live on television and move your little finger. Can you move your little finger? Right, okay. Does your brain have mass? You can weigh your brain, can't you?
Yep.
Yeah. Can you weigh your thoughts?
No.
How'd you move your little finger? Your thoughts are non-material, but they affected this material world. God is spirit, he's non-material. Why can't he just create matter and affect the universe? If our non-material thoughts, our consciousness can affect electrical impulses in our brain, affect nerves and muscles, and through our thoughts we can create things ourselves. We can create a poem, we can create a mobile phone, surely God can create.
So much bigger.
Just like that, speak it into it. It makes more scientific sense than all this evolution rubbish.
It's amazing, really amazing to think about radiometric dating can be so wildly wrong. And if our planet Earth is not billions of years old, but only a few thousand years, that would mean that evolution simply does not have enough time to occur. So that means that evolution is impossible. Now, I realize that could be quite a confronting idea to you, and so I encourage you to get a copy of Dr. John Ashton's book, Evolution Impossible, and work through all of the lines of evidence that he describes in the book. If evolution really didn't happen, could this mean that there's a God out there who originally created this world and loves you? Hang on to that thought as we journey back in time in our next episode to the Big Bang itself. And if you missed any previous programs, you can watch them on our website, 3abnaustralia.org.au. We look forward to seeing you again back at the Big Bang.
Thank you for joining us on Evolution Impossible, a production of 3ABN Australia Television. If you have any comments or questions, send an email to radio@3abnaustralia.org.au or call us within Australia on 02 4973 3456. We'd love to hear from you.